Hello learners, in today's class we'll discuss the design of flanged sections. Flanged section means both T-beams and L-beams as we have discussed in earlier lectures. Now first discuss the codal provisions. Generally these beams are designed as just like rectangular beam sections, single lane post or double lane post. But one of the parameters is the width of the planes that has to be calculated depending on the codal provisions. As far as this shear check is required, same as the rectangular sections, only in place of B you have to take the width of the wave BW. And control of deflection, there is slight change, and development length is similar to this rectangular section. So please open your IS code page number 36, clause number 23.1. where it is written T-beams and L-beams. So we have also discussed what is a T-beam. As you see, what is written in the code, a slab is assumed to act as a compression planes of a T-beam or L-beam shall satisfy the following. The slab shall be cast integrally with the wave, or the wave and slab shall be effectively bonded together in any manner. So this is very important, that during the construction of this beam and slab, they should be casted at a time so that there will be monolithic construction. If you first cast your beam, then put on the slab, they will not behave as a T-beam. This also we have discussed earlier. So either it is a T-beam or beam, and as you know, for a section or a hall, the end beams are generally behave like L-beams, and the intermediate beams behave like a T-beam. The part of beam is taken with the part of the slab. So the part of slab is coming with the wave, and that is why this is called this T-beam. So this part is the width of the planes, and depth of planes is equal to the thickness of slab. So this BF has to be calculated as per the codal provisions. So let us see what the code says. Now effective width of planes, but it says in the absence of more accurate determination, the effectivity plunge may be taken as the following. So go to the next page. (37 to 39). Okay. Now in page number 37, you see what is written. But in no case, it shall be greater than the breadth of the wave plus half the sum of the clear distances to the adjacent beams. That means if you let us see, if there is a beam here, okay. So this is here is a beam, here is a beam, okay, and here is a beam. Now, if you are calculating this effective width planes for this beam, then the maximum value of width of plane will be equal to the width of this wave plus half of the sum of the clear distance. So half of this clear distance not effective, half of the clear distance and half of this. If they are put 3 meters center to center, you can take half of this side 3 meter, half of this side 3 meter. So 1.5 is equal to 3 meter. Or if there are different spacings, then take half of this side and half of that side, and then that is the maximum value of this width of planes that can take part, which cannot be more than that. So the formula is given for T-beams. What is given? BF is equal to L0 by 6 plus BW plus 6 DF. DF is the thickness of the planes, as you know, which is equal to thickness of slab. BW is the width of the wave, and L0 is defined below, that is the distance between the zero moments. That means the center to center distance. And for L beams the same formula, but only here the change is L0 by 12 and here it is 3 DF. So calculate for T beam and L beams the width of the planes. And similarly for isolated beams, you can see for isolated beams what the formula. Isolated means is only one T beam. There is no intermediate beams. So this T beam is equal to BF is equal to L0 by this plus BW, and for L beams the value is given. So you can use this for the isolated T beams. That means it is not continuous beams are provided throughout this hall or in the construction. Now the L0. What is L0? Distance between the points of zero moments in the beam. That means zero moments mean at supports. So if it is simple supported, then zero moments are the ends. So for continuous beam and frames, L0 may be taken as 0.7 times the effective span. If you have a continuous beams of T beams, or if you have a frames, then L0 may be assumed as 0.7 times the effective span. Now, if you see this control of deflections in case of these T beams, what will do? Like your simple supported or cantilever or simple supported or continuous, you take same value like rectangular sections. All these calculations we have done for the rectangular sections, that L by D shall be less than the values given in the code, multiply modification factor. But in addition to this modification factor, and as you know, the modification factor is obtained from this figure number 4, percentage of tension reinforcement versus modification factor. So in addition to that, for flanged beams, written here in the clause E, for flanged beams, the value of A or B is modified as per figure 6, and reinforcement percentage for use in figure 4 and 5 should be based on area of section equal to BF into D. When the deflections are required to be calculated, method is being annexed as C. Now the area of section equal to BF into D, so there are two reduction factors you can see. In case of T beams, the modification factor for compression reinforcement, and there is another factor, that is reduction factor for ratios for the span effective depth ratio in plane section. So what it becomes now, if you write the equation, your L by D ratio shall be less than, suppose simple supported, it is 20 multiplied by the modification factor for this, modification factor for the percentage of reinforcement. So modification factor will find from the figure 4. So depending on your tensile reinforcement, find the modification factor from figure 4. Then there is another modification factor from figure 5. Modification factor from figure 5, and then there is a reduction factor on figure 6. Okay, so all will come depending on the situation. Now you see what is this things given here. So this what is this figure 6? This is giving the plane wave width to the plane width. So calculate BW by BF, and calculate BW by BF, and if this ratio is less than 0.3, you see if it is less than 0.3, then this value will be 0.8 constant, and then if it is more than 0.3 and go up to 1, then the value is go on increasing up to 1. So maximum value is 1. So it is a reduction factor. So that reduction factor is to be applied depending on this BW by BF ratio. Now in figure 5, this is given for the compression reinforcement. So whenever there is a double reinforced section, as we have seen the analysis, if you are designed for a double reinforced plane section, then in addition to these two, reduction factor and modification factor for these tension steels, then you have another factor, that is modification factor for compression reinforcement. So depending on ASC, percentage of compression reinforcement, ASC by BW into D into 100. So depending on this percentage of steel, multiply 100. So calculate this value of PS percentage compression reinforcement and find the modification. Now these factors is also more than 1. They go from 1 to 1.5. So you can calculate this value. This is only applicable in case of if it is a case of double reinforced section or compression steel provided in the section. So double reinforced section, you have to add this value of modification factor for compression steel. If it is only tension steel, then modification factor from figure 4 multiply reduction factor from figure 6. If it is both tension and compression, then modification factor for tension multiplied by modification factor for compression multiplied by reduction factor. So all the three factors has to be multiplied. So this is the control of deflection in case of plane section. But as far as this design of these sections, the plane sections, then the loading pattern is different. What are loadings? If you find for the T sections, what the loads will come? The loads will come from the slab to beam, because it will transfer from the slab to the beams. So first you have to calculate the total load on the slab. So as you know the design of slab, there will be dead load on the slab, self weight plus live load plus floor finish. So add all these values, you'll find the total load on the slab. Now this slab load multiply by the area, or you can find per meter length multiply 1 meter width, you'll find the load in meter. So this load is to be transferred to this beams. So how it will transfer? Let us see one sections. Now you have this beam here, and you have this suppose beam here, and beams are on the 4 sides. It is given also in the your codal provisions. We'll see while designing. Now if you do this distribution of load, this will be at an angle of 45 degree. So this will be the distribution of this load from slab to beam. So this much of area load will come to this beam, this much of area load will come to this beam, and this much of area will come to here, and this will come here, and all these angles are 45 degree. That means the intensity of load you found from this calculation, dead load, live load, and floor finish. This total load in kilonewton per meter square multiply by the area of this, okay, will give the total load in kilonewton. Now this load divided by this span, effective span, will give load per meter length, that is transferred from slab to beam. Now in addition to that, you have to add also self weight of the wave. Self of the wave means BW. So self weight wave means this is BW, and this distance is D minus DF, total overall depth minus the thickness of planes. So multiply this with 25 will give you the kilonewton per meter self weight of the beams. Now this and this weight combined will give the total load that will act on the beam, and depending on that you will find the maximum bending moment depending the support condition. If it is simply supported, WL square by 8, and then if it is shear force, WL by 2. And for this moment and shear, you have to design for these sections for this area of steel as you have done earlier for the rectangular sections. Now once you check for shear, then development check remains same as in case of your rectangular section. Your M by V plus L zeros will be greater than or equal to LD. LD is equal to phi sigma S by 4 tau BD, and you have to then draw the reinforcement detailing. Now before going to this one example of this design of plane section, let us see how we find out this width of effective width of this planes. So let's see how to find out effective length of planes. Some problems on this effective width of the planes. So now we'll discuss on the problems how to find effective width of planes. Now in the first problem, you find a T beam has effective span 6 meter, and with the ends simply supported. Okay, spacing is given 3 meter center to center. Slab thickness 125 means DF is given. Width of rib, it's called rib or wave, both are same. That is for T section, it's 250 millimeter. Calculate effective width of planes. Now you can calculate the value. Width of wave is given, DF is given, L0 is 6 meter. So 6000 millimeter is the effective span given. So you can calculate BF is equal to L0 by 6 for this, depending on the clause number 23.1.2. But in no case it should be greater than the wave plus half the sum of the clear distance to the adjacent on either sides. So that is nothing the spacing of beams, because if you take both sides, it is given 3 meter center to center. So 3 meter means half is 1.5 this side, 1.5 other side. So 3 meter again plus width of the weave, that is 250. So it cannot be more than that value. So you can put the total value will come out to be less than, cannot be more than that. So it is coming 2000, and so but here it is coming 3500. So spacing of beams is maximum than that, so it is less than this. So calculate that value. So the center of this beams, the both sides of the beams, that you have to calculate. And the second example is given. The clear span is 5 meter with the end simply supported. Slab is 100, width of is 200, width of the support is 300 on one side and 200 on the other side. The clear distance of end panel is 2.8 and 3 meter on the intermediate panels. calculate the effective planes for end T beam and intermediate T beams. Now what that means, end T beam and intermediate, that means is like this. Okay, so this is the end T beam. Okay, this is the end T beam and this is the intermediate. So suppose it is going like this way, continuous. So you can find out. So it is continuous like that way. Let it be go like this way. Now this beam, this end T beam means all the intermediate beams are T beams, but this is called the end T beam and this is the intermediate. So what he has given here, that the support is different. You see the clear span is 5 meter and thickness of slab is 100, width of reeve is 200, width of support 300 Newton one side, 200 on the other side. So if it is the 300 side and this is 200 other side. 300, 200. The clear distance of end panel is 2.8. So this 300, suppose this is the wall and this is the wall thickness. Sorry. The wall thickness is one side 300, other side is 200. Okay. That means effective span will be half of this side and half of that side. And also the clear distance of end panel is 2.8. So this is given 2.8 and this value is given 3. Others are given 3. These are 3 and this is also 3. So while calculating the things, you have to see the differences. Let us go to the solution. And the solution, see, BW is 250, DF 100, L0. But the effective span is calculated from this end to this end. So the walls are supported on both sides. One side wall is 300, other side is 200. So take a half of this, that is comes 5250 effective span. Now for end beam, we'll find L0 is equal to 500 plus 300 by 2 plus 200 by 2, that is 5250. Okay, that's same thing. The effective span already have calculated. Now what is the width of planes? L0 by 6 plus BW plus 6 DF. So calculate this value, which comes out to be 1675 millimeter. Now this shall not be more than the spacing of the beams. So you have the 2800 to one side and 3000 other side. So half of this and half of that, and in between there is a beam. So for the end beams, what you do, that this is basically 200 the width, and this side the available space is 2.8 and this side available space is 3 meter. So half of this plus half of this plus this, so that is coming 3100. So effectivity of planes is not more than that, so it comes 1675. But if you come to intermediate beams, then there will slight change, because both side will be 3 meter and 3 meter. This side will be 3 meter and also this side is 3 meter. So the spacing is 3 meter and 3 meter. So depending on that spacing, it will change. Let us see in the intermediate beams what will happen. This BF is equal to L0 by 6 plus BW plus 6 DF. So already you have found L0 5250. Now to calculate the adjacent beams, now the breadth of the wave plus half the sum of the clear distance to the adjacent beams, both sides will come 3000, 3000. So this is the change you see here, 3000 by 2, 3000 by 2. In the earlier case, one side is 2800, other side was 3000. So you should see it carefully. If the spacing of are different, then you take a half up on both sides. If spacing are same, so you can take the value as same on both sides. Now let us go to another problem on this for isolated footing. These are for the continuous T sections. Now for an isolated T beam, has effective span 4.2 meter with ends simply supported. Room size is 4.2 into 6 meter effective. So that means effective length is given. Thickness of slab is 100. Width of reeve is 250. Calculate the effective width of planes. So BW is given, DF is given, L0 is equal to 4200. Okay. So you have to put along the long directions. T beam, so 3 meter distance. So this will be 4.2. This is 6 meter. So you have to put in between. The T section will put here. This is 4.2. Okay. This is 4.2 and this is 6. So you have to provide the beam here in the middle. Single isolated beam. There is one T beam. These are the walls. There is no beams. So it is a isolated T beam. Now calculate the width of planes by put the formula L0. This will be L0. Okay. The effective span is given 4.2 meter effective span. So 4200 and BW is given, calculate the value 1 to 50. So the effective width of flange is coming 1 to 50 millimeter. So these are some of the examples on these T-beams with effective width of flange. In another class, we'll see the detailed design of a plane sections. With this, we end this lecture, and we'll discuss on this design class of this plane section in the next class. Have a nice day.